American Statistical Association. So this is organized by the American Statistical Association Committee on International Relations and Statistics, as well as Statistics Without Borders. And as usual, I just want to thank the people that make this possible. Alex Schmidt, who is basically the leader of this whole initiative. Donna, who makes everything we do possible, and Floka and the rest of the people at Statistics Without Borders. Thank you for your collaboration, and of course my sincere thanks to Erica for agreeing to be the speaker. So she's going to talk about causal inference in statistics, why, what, and how. So Erica Moody is a professor of biostatistics at McGill University and a Canada Research Chair Tier 1 in Statistical Methods for Precision Medicine. She's a research leader in causal inference and dynamic treatment regimes. So thank you so much, Erica, and if you could now share your slides and begin your presentation. Thank you.
Thank you for the kind introduction, and I'd also like to thank Alexandra for inviting me and all of the organizers for putting this series together. And I'll just get myself ready. I'm sorry, I can't yet see my sharing, so just one moment. There we go. Okay. Thank you very much. So I was asked to talk a bit about causal inference, and I've realized, it's an area that I've been working in for quite a long time. And I think there's a lot of mystique around what causal inference is. Sometimes it's seen as a particular method or a guarantee of a particular conclusion that one might be able to make. And so what I'd like to do is talk a little bit about some of the origins. I won't dwell on it too long. Some of the early thinkers in causal inference. And I'll talk a little bit about some of the methods that can be used in very simple settings, really just to give you an overview of what we can do, what sort of focus we have in causal inference, and why this might be important. So certainly the idea of causing or causation has a very long history. Plato himself wrote that everything becomes or changes must do so owing to some cause. So there are thoughts and discussions about what is causation, and indeed philosophers for hundreds of years were discussing what is a cause and different types of causes, whether it was an originative cause. There were religious thinkers as well, thinking about, causation from outside, religious sources versus man-made causes, for example. So there's been a lot of debate about what is a cause and what it means to affect a change. So all of the work that I do, or most of the work that I do in statistics, my applications are in medicine. And so I'm sort of tilting my applications a little more in the direction of things that I work in, although of course these ideas extend to many other fields, whether it is marketing or earth sciences, biological sciences of other varieties. So why would I care about causality? Well, causal inference is used to explain. It's not simply a predictive science, but it's really trying to say, does this treatment or does this intervention affect a change? And these ideas have been used across not just decades, but centuries. So in the very early days of medicine, bloodletting was considered a cure-all, and it was actually a widely established practice. And it wasn't until significant data were collected to really be able to prove that this was in general a terrible idea. This was followed up by other studies that tried to prove causation, not using what we would think of as modern causal methods, but Florence Nightingale was probably one of the preeminent female statisticians, and her polar chart was actually the inspiration for the Canadian Statistical Sciences Institute's logo, trying to show that with better hygiene, mortality was reduced. Later, we've seen randomized trials. So for example, the Women's Health Initiative was an important trial that actually reversed some common knowledge again in prescribing of hormonal replacement therapy And then more recently, there's been work in this Taylor-X schema, for example, is a randomized trial looking at personalized medicine. So how to adapt treatments to individuals. So going from very simple studies of a single exposure that is maybe applied to many, many different causes to much more complex treatment strategies in very narrow populations, we are using these ideas of causal inference, whether from randomized trials or from studies that are not experimental, to try to learn about whether or not an intervention or a treatment is effective, whether it is making a change in our outcomes for individuals. So I lean back on one of my former colleagues, Olli Miettinen, who was really a leader in the field of biometry, who said that epidemiological research is almost exclusively concerned with etiology of illness. So etiology means the causal origin. Where does it come from? And I would argue that the goal of most statistical analyses is to uncover causal relationships. This is, of course, not true in the case of predictive inference. But in many cases, when we are doing regression, for example, really we're aiming not just to see associations, but really to understand whether our predictors are causing changes in our outcome of interest. Unfortunately, it's not very clear-cut. We don't actually have a clear agreement, even within the statistical literature, and certainly across other disciplines, of what exactly causality means. So Udaya Pearl is a computer scientist. He was probably one of the first modern thinkers of causal inference in the sort of modern statistical era, and much of his work has been adopted in the statistical literature, although, as I said, he is a computer scientist. He wrote a textbook on causal inference in which he doesn't ever define causality. He refers to causal relationships as relationships that are stable or ontological, but he doesn't give a precise definition of what causality means. A more recent paper by Meinshausen with Peters and Buhlmann takes a similar view, so talks about causal relationships exist when multiple data sources give invariant predictions. So again, there's this idea of stability or reproducibility is suggestive of something causal, but it's still fairly vaguely defined. So if I go back to some of the earliest ideas in medicine about causality, one is the Koch postulate. So for example, this was used to try to explain bacterial or organismic origins of disease. So for example, here I have a varicella virus, the chickenpox virus, and a miserable little kid. And I think that we would all agree, or it's pretty well established, that the varicella virus is what causes chickenpox. So Koch's postulates, they were a series of sort of rules by which you could establish, or criteria to establish, a causative relationship between a microbe and a disease. And these involve things like being able to find this organism or this microbe in abundance in an individual, or in this case, I believe these are mice that are suffering from the disease, to then be able to isolate it and reproduce it in vitro and reinfect another individual to cause the disease again. So these are fairly well established, but indeed, even these are not perfect in terms of establishing causation. So he applied these postulates to understand the causes of TB and cholera, but there are these gaps. So for example, even in the case of TB, there are latent TB carriers, people who may have the bacteria in abundance, but are not evidently ill. Similarly, there may be asymptomatic carriers of hepatitis C virus. Other examples that don't fit well with Koch's postulates, even for microbes, include things like viruses that are not easily grown in culture. And for medicine more generally, there's a lot of illness that is not necessarily caused by pathogens. So some cancers may be attributable to pathogens, but many are not. And so this is a nice model for microbial disease, but it's certainly not sufficient to understand all the causal origins of disease in medicine. So these are sufficient, but not necessary. So what if we want to learn about non-pathogenic causes? So for example, learning about whether vitamin D is related to different outcomes. So in this case, we might look at daily solar radiation as a proxy for vitamin D exposure and breast cancer mortality. Now here, there's a fairly visual depiction where we see that the states of the US that have higher solar radiation tend to have lower rates of breast cancer mortality. If we want something a little less visual, this study was looking directly at individuals, so not at an ecological level, looking at the odds of breast cancer versus vitamin D as measured in the blood. Again, we're seeing a strong relationship, but how do we know if it's real? Is it causal, or is there something else that explains this difference? And so that's what causal inference tries to do. It tries to provide a set of criteria or a way of approaching a data analysis that lets us try to understand the causes, or whether a cause can really be given a potential cause, excuse me, can be given a causal interpretation, or whether we don't really have enough evidence to do so. Now, moving into more of the epidemiology and away from sort of the lab sciences and the microbes, if we look back to about the 1960s, that's when causality started being described more explicitly in the epidemiological literature, primarily by Sir Austin Bradford Hill. So his article from '65 called The Environment and Disease, Association or Causation put forward a set of considerations. I will not call these criteria. They're often called the Bradford Hill criteria, but Bradford Hill himself said these are not criteria. These are conditions that may help establish causality, but it's not a checklist. These conditions included strength. So the stronger a relationship is, bigger the odds ratio, or the bigger the effect measure, the risk ratio, the difference in means, the more likely a relationship is to be causal. Consistency. So can we see this across multiple different settings? Specificity was really talking about not having these broad effects. So a particular exposure and a particular illness, being able to link these rather than just saying vitamin D is good for everything. It's very hard to assess or establish any causative relationship when we are very broad or vague. Temporality is simply saying the cause must precede the effect. And a biological gradient suggests there's a dose response effect. So more of this treatment or more of this exposure should lead to a greater effect. Then there is sort of this mix of what I would call the generally less useful conditions other than experiments. So plausibility, does the relationship that we're seeing seem to be logical? Does it hold with our knowledge of the illness, of the exposure? Is it coherent with what we know in, for example, animal studies or across other sorts of studies? 8, strangely enough, is experiment. That could be a randomized trial. I always think it's quite funny that this one is so far down on the list, when in many ways it is perhaps what we would consider the gold standard, the strongest possible evidence. And then analogy. So again, are there other diseases that work in the same way, other treatments that are similar, and we can make a reasonable analogy? So of these, probably I would say 1 and 8 are the most reasonable. Experimentation, where we can remove any concerns about what's known as confounding, which I'll talk about momentarily, and strength of association. Strong relationships are hard to explain away. So these are probably the 2 strongest. Temporality, of course, is also a must. Your cause really must precede your effect. So less well known is Bradford Hill's lecture on the statistician in medicine. It's a brilliant article. It was just republished 2 years ago as part of an anniversary. And in this article, he talks about, or this lecture really that was reproduced as an article, he has 3 main themes. So one is the importance of the area of application. And this is something we'll come back to in thinking about causal inference. We can't just have X's and Y's. It's critical that we understand the context of the problem that we are working in. He talks also about the types of data that we use to provide evidence and how those data are gathered, including what he calls the poor experimenter that is nature. In other words, non-experimental or observational studies. And then he talks about how we can use these things to draw conclusions from our evidence. So I'm going to come back to this article at the end of the talk, because although it's from quite a long time ago, the ideas in it maybe less formal, are nonetheless extremely relevant to the most modern era of causal inference, which is often known as the counterfactual framework. So the most significant challenge that we face in causal inference, or probably the one that is most often tackled by these methods, is what is known as confounding. So confounding is an idea where there is some variable that is related to both our exposure of interest and our outcome that might explain the relationship between the two. So there is a classic sort of study that was done many years ago that looked at the rates of chocolate consumption and Nobel Prizes per country. Found an extraordinarily strong relationship, very strong correlation between these two things. And I like to go back to this idea, does eating more chocolate make people brighter? Maybe, maybe not. It's hard to say. There are lots of good things associated with cocos, flavonols, antioxidants. Maybe that makes me smarter. I would be happy to believe it. I do like chocolate. But there are also alternative explanations. It may be that countries with higher rates of chocolate consumption are also countries with higher GDP, perhaps better educational systems. We don't know, right? There are lots of alternate explanations that we could think of that would explain this strong relationship that we see. That is confounding. Something confounds or confuses or muddles an association so that we can't really say whether it is the treatment causing the exposure or just something else that is related to them both. There are, of course, other types of biases that exist in data. We could have missing data. We could have measurement error, or what's known as selection bias or participation bias, so that the data we observe is not representative of the population that we would like to apply our inference to. In many ways, the ideas that I'll talk about today, although they focus on confounding, can easily be applied to these other forms of what I will call data imperfection. So again, the goal of causal inference is to identify and address, either through design or through analyses, these challenges of data imperfection. So the Rubin causal model is one method of doing this. And this Rubin causal model, also known as the counterfactual framework, really dominates the statistical literature on causality. It is not the only framework. There's an entire counterfactual free version of causal inference, but it is the main one that you will come across when reading articles on causal inference. It's so equivalent to, as I said, the counterfactual framework, or also called potential outcomes framework. And these ideas are actually often attributed to Neyman, who did work in agriculture, looking at what happens with the application of different fertilizers to fields and imagining, had he applied a different fertilizer to a particular plot, what might the yield have been? So that's what we're doing with these potential outcomes, or these counterfactuals. We're coming up with hypothetical or what if outcomes. What would my outcome be if I ate a lot of chocolate versus what would my outcome be if I refrained from all sweets? So this framework supposes that each individual has two potential outcomes. If I'm working in a case of binary treatment, so, two levels of treatment that I'm coding 0, 1, then I have two latent outcomes, two potential outcomes that could be observed. But I'll only get to see one of them because I will only experience one treatment. And that's where the challenge lies. If I could observe both of these, then I could look at the difference, and that would tell me exactly whether there was a difference in my outcome based on being treated differently, right? Because everything else about me stays the same. The only thing that is changing in this counterfactual framework is the treatment or the intervention that is applied to me. But my age, my genetic background, my family history, my education, the neighborhood in which I live, all of these things would stay fixed. And so the only difference is given by the treatment applied to me. But as I said, we don't get the luxury of seeing both of these. So fundamentally, most of the biases that will impede causal inference can be viewed through the lens of actual missing data rather than confounding, because I can see that I would love to observe both of these, but I only get to see one. So how do I deal with the fact that I only get to see the outcome in one treatment condition. So at an individual level, I can think about these contrasts and counterfactuals. I can think about differences between counterfactuals. What would happen to me if I ate chocolate versus whether I did not? But I can never observe that because either I eat the chocolate or I don't. So what good are these counterfactuals? Well, they help us think about what it is that we are trying to fix and remind us that we cannot be allowing other things to change simultaneously. We want to only manipulate one thing in the system, and that's our treatment of interest. Now, of course, because I can't do this at the individual level, and because we're statisticians and we work with populations and samples, we do this at an average level. So we can define causal effect of an exposure or treatment by considering contrasts between population level averages. So a common estimand or a common target of interest in causal inference is what's known as the average treatment effect. So we want to estimate the average outcome if everyone in my population was given chocolate or exposed to my active treatment, and what would happen if it was withheld from everyone. So really what I'm allowing for is the fact that effects may differ between people, and I'm going to be marginalizing over the distribution of treatment effects in my population. So these are not conditional effects. These are truly population average effects that imagine a world where I could give or withhold a given treatment from my entire target population. So I'll be focusing primarily on this difference in averages, but we can think of other types of contrasts as well. So for example, ratios or multiplicative differences. This can also be done on the odds ratio scale. Okay, so we can think of confounding in terms of Rubin's causal model. It's likely to appear whenever my pair of counterfactuals is not independent of my treatment Z. So what does that mean? It doesn't mean that my outcome and my treatment are independent, but rather that treatment is not allocated in a way that is knowledgeable of how an individual would respond to that treatment. So for example, I am not preferentially giving treatment to sicker patients because I think they need it more. Or I'm not preferentially giving the cheaper treatment to patients or individuals with lower socioeconomic status because I think they can afford it less, because doing that could introduce other biases. They may have different diets, they may have different environmental exposures. So the idea is that treatment is allocated independently of how an individual would respond to that treatment. Okay, so we have confounding whenever that doesn't hold. Okay, so this tends to happen. We have this idea of confounding whenever the treatment hasn't been determined through complete randomization. Okay. Generally speaking, treatments are allocated by physicians or by policymakers, or indeed chosen by individuals. I may choose how much sun exposure I have or how much chocolate I eat. So these happen in non-experimental ways or observational studies. Okay. So if that's the case, then it may be that how I respond to treatment and the treatment I receive have common determinants. And if that's the case, then my treatment will be informative of my potential outcomes, even if the treatment itself is ineffective. So we can think of this idea of confounding in a loose sense as occurring whenever my treatment or my exposure and my outcome have a common cause. Okay, so it may be that chocolate doesn't make me any smarter. However, if I have lots of disposable income to spend on chocolate, that might also buy me a house in a neighborhood with less pollution. It might buy me access to more vegetables that I eat alongside my chocolate. It might give me access to other things that are good for my health or good for my academic outcomes, say. So it may be that this relationship between my socioeconomic status and my chocolate eating is providing what we call a backdoor path from my outcome to my exposure, even if there's no effect of my exposure itself. This is, again, to give another concrete example, the vitamin D example. It may be that socioeconomic status determines vitamin D exposure. That could be because of the type of work somebody engages in. So whether it's outdoor labor versus an indoor job, or whether it's being able to afford sunny holidays if you live in somewhere sort of frosty like Canada. So it could be that there's this common determinant, so that even if vitamin D has no impact on cancer rates, that we appear to find a relationship because of this backdoor path through socioeconomic status. Okay, so that's what we're trying to define when we're looking for confounding. And this is what I mean when I talk about the importance of context. Okay, if I have an exposure and an outcome, who knows if I have common causes? I can only start to think about this if I think about the specifics of what my exposure and my outcome really are. I need to know the context to be able to start thinking causally about the structure that underlies my data and what it is that I need to worry about or account for in my analyses. All right, so maybe I've been lucky. Okay, I'm working in a setting where my data are not experimental, but I managed to record all of those common determinants: socioeconomic status, the neighborhood I live in, the other foods that I eat, the exercise I do, and the sunscreen that I wear. So all of my other common determinants have been recorded, and I'll call these covariates X. Okay. So I can get myself back to an independence assumption simply by conditioning on X. So if I say that within any group defined by these covariates X, I have independence of my treatment and how I will respond to treatment, my pair of counterfactuals, then we think of this as controlling for confounding or restoring that independence. So we now have conditional independence between the treatment and the counterfactuals. So there are many different names that this conditional independence term has been given. Sometimes it's called exchangeability, sometimes it's called strong ignorability. I'll call it the no unmeasured confounding assumption. I assume that any confounding that exists, I have accurate measurements of those confounders X. Okay, so no unmeasured confounding means not only do we have confounders, but that they're measured. Carolina, do I have a question?
Okay, I thought we might take a little break to answer a couple of questions that came up on the feed. So one of them is from Erica Kai, a hypothetical. I think so. It says, "Hi, Dr. Moody, nice to see you again. I met you at 2 conferences in Southern Ontario in the past." So I think then this is a hypothetical. "I am selling pizza at 1,000 stores. Today I will launch a buy one, get one promotion at 100 pizza stores. The other 900 stores will not have this promotion. I have data for all the confounding variables that you want to measure, but I do not have any sales data before the launch of this buy one, get one free promotion. Thus, I cannot use propensity score matching in the pre-intervention period to find suitable control stores. My question, under this limitation of having only post-intervention data, what technique from causal inference can help me to measure the average treatment effect of my buy one, get one free promotion?"
Well, I think I need to unpick this one a little bit, because if you have all confounding variables, that implies, if I go back a moment here, if you have all confounding variables, that implies that you have every pre-exposure variable, so pre-BOGO intervention, that is predictive of being a buy one, get one free store and of the subsequent sales. Okay, so the no unmeasured confounding, you said that you have data for all the confounding variables I want to mention. That means that you have information on anything that has made the store be selected, those 100 stores that allowed you to choose those to be the 100 stores in which you would run this intervention. Okay, so if you say you don't have any sales data before the launch, then that implies that that is not a confounder. So as long as those sales data from before the launch are not a reason for selecting a store to have this BOGO intervention, then you're fine. Okay, missing, maybe I can draw momentarily. Here we go. If I have, I'm going to call this a P precision variable here, something that affects my outcome, but doesn't affect my exposure, That's not a confounder. Okay, so if these pre-sales data might affect my sales volume after, these are bigger stores, but they don't affect whether or not I put the promotion in that store, then it doesn't matter. It's not a confounder and I don't need it. Don't need it for causal inference. If my pre-sales data is truly a confounder, so it affects not only my sales volume later, but also whether that store was selected as a buy one, get one free, then we don't have unmeasured confounding. And the methods that I'll be talking about today can do basically nothing because they assume that we have no unmeasured confounding.
Great, thank you.
Great.
Thank you for that. There are some more questions. So anonymous attendee says, for me, it is complicated to understand this topic. As a chemist, I work with millions of molecules, individuals, but they behave always the same. We provide some correction factors as yield or effective coefficients, but A plus B will always produce C. This approach is mostly targeted to biological samples from cells to humans. So that's the question, that last part.
I am hesitant to answer because it is definitely outside of my, I definitely don't work with molecular samples, but if A plus B always produces C, you have a deterministic relationship. And so there's not the same need for the sorts of regression that we are doing. If A plus B always gives you C, then A plus B causes C. Where we're working or where these methods that I'm talking about are applicable is in cases where A plus B doesn't necessarily always cause C. Maybe it shifts it up, maybe it shifts it down, but there's also D, E, F, G moving around in the background in ways that may be related to A and B and C. So it's sort of not that deterministic relationship. So I'm not sure if I'm answering this question well, but if there is something deterministic where doing something always produces a given result, I don't think that the methods that I'm talking about would be applicable. I see about stratification. We'll get to stratification. And there's another question about the differences between confounding and mediation and moderation. So that one, I'm going to skip over stratification because we get to that later in the talk. The difference between confounding and mediation. So a confounder is something that occurs before the exposure. It is a pre-exposure variable that is affecting both the exposure and the outcome. A mediator, on the other hand, is something that lies on the causal pathway between your exposure of interest, sorry, I apologize for my messy writing, and my outcome. So a mediator is a mechanism by which the exposure or the treatment is affecting the outcome. Sometimes we can decompose the effect of an exposure on an outcome into the path that goes via this mediator and other pathways. So the mediator always comes after the exposure, the confounder always comes before. Moderators are a little bit tricky. Moderators are often called effect modifiers. These are things that will change how the exposure works. So it may be sex is a common moderator or effect modifier. So it may be that treatments behave differently in men versus women, for example. And let me just see if there are any more questions that I've missed before I carry on. Is there a notion of a partial or poorly measured confounder? Yes. So a poorly measured confounder could simply be a confounder that has measurement error. So blood pressure would exactly be a good example of that. I won't get into the details of this today, but depending on how that confounder works, there are different ways that we might want to adjust for it. So if the mismeasured version of the blood pressure, for example, is used to make the exposure decisions, we tend not to make any adjustments for the measurement error. Whereas if it is the true variable, not the mismeasured version, that is affecting our exposure, we do need to make some corrections for the measurement error. Sometimes we also have surrogates, so they're correlated with the true confounder. We can again view this as a mismeasured version of the true confounder, but understanding that structure and whether it's the true version or the mismeasured version that is really leading to the decisions about the treatment is important. And just to think about this, like in a medical context, suppose we have a noisy measurement like blood pressure. Well, that noisy measurement is what the physician is seeing. So that noisy measurement is actually the true confounder in a sense, because it is that noisy measurement that the physician is basing their treatment decisions on, not the true underlying blood pressure. Okay, so it can really depend on the specific context, whether you need to address or correct for the measurement error or not. Let me see. In principle, if we can directly observe all conceivable backdoor paths, then there is no confounding issue. This is true. If we have all confounders, we can adjust for them via various means. We will talk about some of these means later. How and when can we be sure that we've controlled for all paths? You can't. It requires faith and a deep understanding of the context of your question. Okay, so knowing that you have all measured confounders is difficult, but deeply understanding, again, the specific problem that you are working with, speaking closely with clinicians, with public health researchers, whoever it is that you're working with or in the substance area, will help you identify the most critical confounders. Usually, big confounders have big effects. Small confounders, ones you might not know about, are less likely to dramatically bias your results. What is the difference between a latent variable and a confounder? A latent variable, latent is by definition something we haven't measured. So you may have latent confounders or unmeasured confounders, or you can have measured confounders. So a latent variable is simply something that isn't measured. We can have latent confounders, we can have latent precision variables. So as I said, a variable that affects the outcome, but not the exposure. Latent simply means unmeasured. Confounder specifically refers to this idea of a variable that is causally affecting both the exposure decision and the outcome. Are the arrows always unidirectional? Yes. Does this limit the framework? I would argue no. Because, well, should I say this? There are sometimes bidirectional arrows put in. Generally, that occurs because you don't know a relationship. So a bidirectional arrow often means that there is some correlation, but I don't know why it's occurring. I don't know if it's because one variable affects the other or vice versa, or maybe they have some common cause that I'm unaware of. So generally, we try to build these as being unidirectional. And this is what's known as a directed acyclic graph or a causal graph. So we try to avoid cycles, because if we have cycles in these, then we simply can't untangle the relationship. But I should note that if we're thinking about longitudinal processes or things measured over time, then we can simply unravel the time effect, right? So that we have measurements or these unidirectional graphs at each time step. Good books in order to understand this better, probably, there are lots of good books. There's a primer by Nick Jewell that I think is fantastic. There is the book What If by Miguel Hernan and Jamie Robbins, which is freely available on their website. Those are the two that jump to mind, but there are probably other good ones as well. I would say those are the best places to start for statisticians. Udea Pearl's book is a useful resource, but it is really not aimed at a statistical audience. Okay, I'm going to grab a sip of water, and I think that we will carry on if I may. Okay, so the idea behind confounding is that without adjustment, an estimator that's just based on simple averages of the exposed and unexposed would be biased in terms of estimation of an average causal effect. So we can think about this as, imagine comparing everyone who eats a lot of chocolate versus everyone who does not. Well, they differ in a couple of ways, right? They differ in their chocolate exposure, but they probably differ in other ways too. Maybe the chocolate eaters have more disposable income. Maybe the chocolate eaters have more cavities, and that can be leading them. So oral bacteria has been associated with cardiovascular disease. Maybe the chocolate eaters, I have a larger BMI. So there are lots of ways in which my chocolate eating group and my non-chocolate groups may differ. And so a simple comparison of averages could be very misleading, because I can't necessarily attribute it simply to the differences in their chocolate consumption, because they differ in all these other ways. I should just point out briefly that even in a randomized study, we sometimes have imbalances. Usually these are just due to chance imbalances, which are more likely in a very small study. We tend not to worry about them, but if we do see big imbalances just due to chance in a randomized study, we often want to adjust for those too. Okay? Because the idea of randomization providing balance in all of our potential covariates, it's true on average, it's true in large samples, but it may not be true in a given single randomized trial. Okay, so there are many writers working in this counterfactual framework that add an additional restriction, which is that to really perform causal inference, we need an exposure or treatment that is manipulable. It is something that can be given or withheld. So there's this mantra that is often repeated that there is no causation without manipulation. Okay, so that means that we cannot perform causal inference on age. I cannot magically change anybody's age. Okay, I cannot perform causal inference on biological sex at birth, right? Again, this is not something that I can manipulate or change in individuals. There are studies that have attempted to look at the impact of sex by, for example, sending out CVs with different obviously gendered names. So in that case, the CV's name has a gender that can be manipulated, but in terms of actual individuals, in a, say, in an observational study of vitamin D, this is not something that I can do. All of the methods that I talk about can be applied to any sort of exposure, but it's more about the sort of interpretation and whether there are things that come along with that exposure or that factor of interest that can really be untangled. So could you really think about a counterfactual version of me that was not a woman, for example? I don't know what other things I would be different were I biologically a boy at birth. So this idea of manipulation is often stated mathematically in terms of what's known as the positivity assumption, which states that for all of our covariates of interest, all of our potential confounders, there is a positive probability of receiving the 1 level of treatment or the 0 level of treatment. So nobody's treatment is deterministic as a function of their covariates. So even if some groups of individuals as defined by their covariates are more or less likely to receive the active treatment, there is no group of individual for whom it is impossible to receive either level. Okay. So we need to be able to observe the conditional means of our outcome at every possible combination of treatments and covariates. And part of the reason, one way of thinking about this, is it just avoids extrapolation. If there are certain combinations of covariates for which everyone always receives the active treatment, well, I can't possibly hope to learn about a treatment contrast unless I'm extrapolating, because there's nothing in my data that tells me about how treatment acts in that subgroup of individuals. So this is also known as the overlap or the common support. And I like to think about this very much in terms of extrapolation. So if we think about, our first regression class, right? We have a cloud of data here, and you fit a regression line through it. And then your prof says, okay, I would like you to give me an estimate or a prediction for my outcome at this level X. And you say, okay, I go up to my straight line and I see what my predicted outcome would be. Great, no problem. What if your prof says, now give me a prediction at this level of X, way out here on the right-hand axis? I can do that. I can extrapolate my regression line out here. I can give you a point estimate, but we all know, looking at this graph, that I have no data out here So there's an awful lot of faith being put into my model to be able to make that statement. The common support is really the same idea. What we're saying is that we need data. We need data on both treated and untreated individuals in every possible area of my X distribution to be able to make a contrast between the treated and untreated individuals. So this is an example of the sort of thing we could do to check for common support. So here I'm looking at the distribution, a density plot of my confounder for two different levels of treatment, the solid line and this sort of dashed line here. And we can see there's a shift in the distribution. So the solid line tend to be a little lower on that confounder distribution, a little bit higher for the dashed line, but broadly speaking, there's good overlap in the density of this confounder across the different levels of my treatment. So this is a case where, based on this graph, I would say positivity appears to be holding. Okay, my assumption is not violated. So being able to identify a causal effect means that I can use my observed data to define a causal parameter, such as an average treatment effect, in terms of my potential outcomes. So the key assumptions I need to make are the no unmeasured confounding assumption and this idea of positivity or overlap, assuming I have common support in my X distribution or my confounder distribution for my two levels of treatment. So if I can make those two assumptions, then I can estimate my average treatment effect as the expected difference in these counterfactuals. What would happen if I treated everyone in my population versus nobody? And I can do this simply with my observed data. I do it by conditioning on my other covariates. So I can look at my expected value of Y given treatment equals 1 in my covariates, and I subtract from that my expected value of Y given no treatment in the covariates. Okay, I know that I have common support across my X's. And if I have no unmeasured confounding, then my observed outcome is equal to my counterfactual outcome. Okay, there's nothing unusual going on there. Then I can simply take my marginalization over X. Okay, so we can actually connect our counterfactuals to the observed data when we have no unmeasured confounding. So these two assumptions, no unmeasured confounding and positivity, are really sufficient for non-parametric identification. I don't need to make any further parametric models. But in practice, we do use modeling assumptions. We might use regression on our outcome model, a model for Y given Z and X. You can imagine that if X here is continuous or high dimensional, I have a number of covariates, I don't want to simply try to estimate this non-parametrically. I'd like to put some sort of smooth structure on it, like a regression model. So I can have a regression model for my outcome, or indeed, I can use this other component of my likelihood, which is known as the propensity score. That's a model for my treatment or my exposure given confounders. So I'll talk about how we can use these different components to estimate causal effects. There are lots of different ways of doing this, though, and that's one of the key takeaways from today's talk. Causal inference is not using a propensity score. Okay? It can be, but it doesn't need to be. We have lots of different ways of adjusting for confounding to try to estimate true causal effects. These can include regression. So if you've done a linear regression and you included all of your confounding variables and you thought very hard about what your model looks like, you've done causal inference. We can use stratification and matching. We can use reweighting. There are lots of different ways that we can achieve a causal interpretation. Okay? The main goal is to recreate a data set that looks like a randomized study by trying to create balance between our treated and our untreated groups. Our two levels of treatment, we want them to look as comparable as possible with respect to the confounders. Why? So that when I compare my chocolate eaters and my non-chocolate eaters, that's the only thing that's obviously different between them. Okay, I want to compare chocolate eaters and non-chocolate eaters who are similar with respect to anything else that might matter, like socioeconomic status or BMI or other parts of their diet. So the effects of treatment are commonly analyzed through regression models. This is probably the first major statistical technique that you use once you move beyond t-tests. Okay, we might have a linear regression model that looks like this. I've got an intercept, I have my effect of treatment here, and then I've got adjustment for all these other potential confounders X. Now, if this model holds, okay, if I've correctly specified this model and it's an accurate reflection of nature, then my causal effect is constant over the covariates because this model here does not include any treatment covariate interactions. If this is true, then this parameter beta actually represents my average treatment effect. Okay, beta is simply looking at, maybe I'll start here. Okay, I've got my expected difference in counterfactuals, which I can represent as the expectation of my observed outcome given treatment and covariates. If my model is correct, then I can simply plug in my model and I'm left with beta. Okay, so if I have correctly specified my outcome regression model, and when I say correctly specified, I mean I have included all of my confounders and I've correctly specified the functional form. If there's squares, if there are splines or other flexible terms, they're all included in this model, then my regression estimator is giving me what I want, which is an estimate of the true causal effect, the average treatment effect. Okay, so we have this nice direct interpretation of beta, my regression parameter, in an outcome regression model as an estimate of an average causal effect. Okay, brilliant. If you can do regression in a correctly specified model and you have no unmeasured confounding, you can do causal inference. Some caveats. It's only valid for a linear model with a constant additive treatment effect, so no interactions. It does rely on correct specification of that model. And again, when I say correct specification, I mean capturing what's going on in nature. The other sort of tricky thing is there's no warning given if the overlap assumption isn't satisfied, and it's rather hard to assess balance. So that's not to say you shouldn't do this, but I'm just saying it's harder to assess whether our causal assumptions are actually being met. So what if we had non-constant causal effects? We have some sort of interaction. Okay, so consider a simple model where I just have an interaction with one covariate X1. Okay, so I've got my main effect of treatment, but that effect is also moderated by the covariate X1. We've got this interaction term. I can no longer interpret beta as the average causal effect. Right? If I look at my expected difference in counterfactuals, and I plug in my estimates based on the model, I see that what I end up with for my average treatment effect is beta plus the coefficient on the interaction times the mean of that covariate X1. So I can still derive an average treatment effect from my regression model, but note that I do need to again specify these interactions if they exist. We could have a more general model. It needn't be a linear model. We could simply have some regression model, potentially nonlinear, that is specifying the dependence of my mean outcome Y on my treatment Z and my covariates X. Okay, so I have a conditional mean model, not necessarily linear, no problem. I estimate that model using my favorite fitting method. And then what I can do is take the observed covariant values in my data set and get an estimate of what that mean outcome would be for that covariant pattern if that individual was treated. And I do that for everyone in my study. Okay? And I do the same thing, but now as though everyone in the study was not treated. So essentially what I'm doing is I'm saying I'm going to specify a model for my outcome. And I believe this model. I think it is a representation of nature. If I believe this model and I estimate its parameters, then I can use this model to provide predictions for my expected outcome for every individual under either treatment condition. So that's giving me a prediction of my counterfactual outcomes for each individual. These are conditional effects. They condition on X. So if my target of interest is this marginal causal effect, this population average, no big deal. I can just average out. I take an empirical average over my sample of these predictions for the potential outcome. Okay, so that's how easy causal inference can be, with the caveat that you really do need to specify that model correctly. It needs to be sufficiently flexible. So there are some certain drawbacks that are associated with regression, and this is why much of the causal literature is shied away from regression. We worry about model specification. Okay? It does rely on that model being correctly specified, and it can be difficult to really quantify whether we have good balance between our treated and untreated individuals, and indeed difficult to assess whether we have overlap. So regression doesn't give us any warning signs or red flags if there are areas where there are no treated individuals and lots of treated individuals for certain spaces in the certain areas of the covariate space. Okay, so those are some of the warnings, but again, carefully done. This can be used for causal inference. We also have many advantages. So we are familiar with regression. We have well-established theoretical models. We have lots of flexible models if we're concerned about that model specification. And then we can easily implement these average treatment effects by simply predicting counterfactual outcomes for every possible individual in our sample or any covariate combination that is of interest. It's equally easy to look at conditional effects. So if we wanted to look at subgroup effects, effects in people 18 to 25, easily done simply by doing this, averaging only among individuals that fall within that specific subset of the population. But what are other ways that we can use to control for confounding? So the propensity score is a term that is often used, and it is probably the most commonly used method of controlling for confounding in the, what I would call the non-regression causal inference literature. We see this term propensity score a lot. And what it is, or its most common definition, is the probability of treatment given the covariates, often fit by a logistic regression when we have a two-level treatment, z equals 0 or 1. The real definition is a little bit more nuanced than that. It's not just the probability of treatment given a whole load of covariates, but in fact, it's the probability of treatment given the confounding variables. Okay, only those things that predict both the treatment and the outcome. So the true definition is that it is the coarsest possible balancing score. It gives us balance, or it gives us equal distributions of our confounders in the treated and untreated groups, but it doesn't unnecessarily stratify our two groups. So there are two important results that come from the propensity score literature. The first is simply that the propensity score is a balancing score. And by that, I mean that conditional on the propensity score, the treatment and my covariates X are independent. Okay, so my propensity score E of X adequately summarizes all of the information in the confounders such that once I condition on it, I no longer have a dependence between X and Z. So what does that mean? Well, we said that confounding happens when I've got a relationship between X that is predictive of both my exposure and my outcome, right? And this is the problem of confounding. It's this backdoor path between my outcome and my exposure. But if I can condition on the propensity score, it removes that link between X and Z. And by removing that link, I no longer have the backdoor path between Y and Z. Oh, is it time for questions?
Just taking a few questions. There's one in the chat, and then there's a few in the Q&A. The one in the, I can read you the one in the chat. It says, when predicting counterfactual outcomes, do you use the real outcome for the treatment received and the predicted outcome for treatment? Yeah,
you can do either one. Either one is entirely possible. So you could predict the counterfactual outcome, both counterfactual outcomes for every individual, Or you could simply use the observed outcome for the observed treatment and predict the missing variable. Either one is equally valid. That's a great question.
Okay, and then there's some in the Q&A. It's good to read them, I think. I'm not 100% sure they can see it.
Yes. Okay,
so
I'm still coming back to the stratification, so I'm still not ignoring you. I'm promising that I will get to that soon. What are the most common techniques to deal with latent variables? I'm going to take a pass on this question. I apologize, but that is really far outside of what we're going to talk about. So, oh, Alex will answer this question. Thank you, Alex.
No, actually, I was just putting done. I agree with you all. Latent structures are so general. It's hard to address this question.
So there's another question that says the goal is to isolate the variables that change the outcome and the magnitude of that change. Yes. And one of the key ideas in causal inference is to really focus on one potential treatment or one potential cause at a time. And the reason we do that is because for any given treatment outcome relationship, we need to think about the confounders of that specific relationship. So while we might do causal inference on a number of different potential causes, each one requires its own analysis to really think through the potential confounders and the potential pitfalls of that particular treatment outcome relationship. Let me see. Since all models are wrong, but some are useful, what steps or metrics do you recommend we take to be reasonably sure we're measuring the correct underlying nature and our chosen causal inference model? So if we are doing outcome regression, you should do absolutely everything you were taught in your first regression course, by which I mean check all of your residuals, make sure you're doing everything you can to assess the fit so that it's clear that you've done the best job you possibly can. If you are taking a propensity score route, then we will see some of the tests and checks that you can do momentarily to help assess other forms, such as, for example, the overlap or positivity assumption. We're able to assess that using propensity score methods, which is something that is actually very hard to assess using regression methods. As for the no unmeasured confounding assumption, I was asked about something, that question a little bit earlier, and I sort of said that you kind of hope and pray. That is really what we do need to do with no unmeasured confounding. We hope that we understand the context well enough to know whether, there is a big confounder out there and that we have indeed measured it. But it's a little bit like the missing not at random assumption. It's pretty much impossible to test for it with the data you have. The only way we can really assess it is through knowledge of the context rather than through testing with the data at hand. Okay, I think that is, can we distinguish between covariates and confounders in a regression analysis? Oh, that is a tricky one. I think I'm going to come back to that one at the end because I'm a little bit wary of running out of time, if I may. But in a regression analysis, no, maybe I'll answer that now. If we go back to a regression analysis of this form, okay, I've got my treatment Z. I have other variables that I am adjusting for. Those variables could be confounders, or they could be other variables that predict the outcome. And we may want to include those really to drive down our residual variance. Okay, so we can adjust for things other than confounders in a regression analysis, and it doesn't matter what we call them. Okay, and we do need to make sure we get all confounders in there. Adjusting for other things that reduce our residual error, great. Doesn't matter what you call it. But what does matter is that we cannot interpret the coefficients on these covariates in the same way that we can interpret the coefficient on our treatment. And the reason for that is that when we have built our conceptual model or our causal diagram, we've been thinking about Z as the exposure of interest, and we've been thinking about these X's as things that precede Z, that are temporally, earlier in time. Okay, so we are thinking about adjusting for the confounding of the relationship between Z and Y. But if we try to think about X, well, X is something that came before Z. So if we're trying to interpret this coefficient on the X, we're in a bit of trouble because now we've got variables in our model that lie on the causal pathway from X to Y. Okay, so when we're doing causal inference, this is what I mean by focusing on one exposure at a time. If we're interested in other exposures, we need to again think about the confounding relationship for that exposure and the outcome. And it may be different from the ZY exposure. All right, I'm going to hop back to my propensity score here. Okay, so as I mentioned, the propensity score, this model for treatment given the confounders, it summarizes all of the variables, all of the confounding variables into a single univariate score. If you've got 1 or 2 confounders, you don't really need a propensity score. If you have 10 confounders, it can be very useful to have a single one-number summary of all of those confounding factors. And because the propensity score is what we call a balancing score, it gives us balance in the confounder distribution between our treatment groups. Conditioning on that propensity score gives us the balance we need. So what it tells me is that the distribution of my confounders, when I condition on my propensity score, is the same in my 2 treatment groups. And that's what we would want if we were trying to mimic a randomized trial, right? In a randomized trial, what we want is that all possible X's, not our treatment, but all other possible covariates have the same distribution in our 2 treatment groups, because we want the only things that differ between our treated and untreated to be that treatment and nothing else. Because if nothing else differs between them, any differences that we note must be attributable to the treatment. All right, so we can use the propensity score for estimation of a causal effect. If no unmeasured confounding holds, I really do have all of my confounders contained in X, the propensity score is enough to control for confounding. Okay, rather than adjusting for all 10 or 20 or 50 confounders, I can just adjust for the propensity score, my one-number summary of those 10 or 20 or 50 variables. Because given my propensity score, I now have independence of my treatment and my counterfactual outcomes. So that gives me a simple strategy. I can now do a regression, for example, of my outcome on treatment and the propensity score, and I can make that as flexible as I wanted to. That's one way that I could adjust for my confounders using the propensity score. So this would be known as propensity score regression, where I replace my many, many confounders with my single one-number summary, which is the propensity score. Okay, so that's what I could do with propensity score regression. I treat my derived variable, my propensity score, as a covariate in my regression model. So rather than adjusting for each of these X's individually, I adjust for this function of the X's. I could also include those X's separately if I wanted to, but I don't need to for the purposes of controlling for confounding. So if I have correctly modeled my propensity score, then an ordinary least squares traditional straight up regression estimate is consistent for my conditional causal effect. So my treatment effect among those individuals defined by a given propensity score. I apologize, that's lousy notation. Maybe I need a big E of X here. My propensity score is a certain value E. I apologize for that notation. Now, again, in the case of no treatment covariate interactions, this regression model would give me an estimate of the average treatment effect. The beta here is an unbiased and consistent estimator of the average treatment effect if I've correctly specified my propensity score model. Okay, this is only true in the linear model setting. For more general GLMs with non-identity link functions, propensity score regression actually provides only approximate confounder elimination. It helps, but it's not quite all. We have other approaches too. So I promised you I would get to stratification. This is one way of doing it. So the stratification estimator is a weighted sum of differences of sample means across strata. So you may be familiar with the idea of stratifying by age and sex, right? We might break down age into 3 or 4 groups. We have 2 biological sexes, or often defined as such, or we may have, you know, male, female, and non-binary or other definitions, but we usually have a relatively small number of strata when we are looking at stratification. Okay, and the idea would be that by looking within these strata, we are looking at individuals who are in some senses similar, okay, similar in terms of their covariate profile. And because they are similar in that covariate profile, they should not be, confounded, right? They are similar in age, they're similar in sex, similar in socioeconomic status, and therefore what is different between these two groups in a given strata would only be the treatment. So that's the idea. We define strata, and we can look at simple averages within the strata, and then we take the average of those averages, again, weighting them by the size of the strata. So the bigger strata carry more weight. Okay, now we can do this based on covariates themselves. Like I said, age and sex is common, but we can also do our stratification based on the propensity score. So we can fit our propensity score. It's a probability, so it lies between 0 and 1. And we can discretize that. So for example, we could cut our propensity score into quintiles. We have 5 groups, and we look at these averages among these 5 strata. The advantage to using propensity score to stratify is it allows us to stratify while taking into account a large number of covariates, because our propensity score is a 1-number summary of as many variables as we can fit into our regression model for the treatment given the covariates. Okay. But the idea here is really fairly straightforward. If you're interested in a stratified estimator, you're really just comparing simple averages. Okay, we don't even need any regression. We are simply computing empirical means within the strata and then reweighting these to ensure that the bigger strata carry more weight because they have more information. What about matching? I think of matching as the finest possible form of stratification. So when we're stratifying on the propensity score, we're trying to compare the 2 levels of treatment within the same interval of the propensity score, because that corresponds to similar levels of the covariates. The finer our strata, the less bias we have. The bigger our strata, the more bias we have, because within a given stratum, we will have individuals who are less similar than they might be. Okay, so there's still some remaining imbalances when we look at stratification estimators, particularly when we have few strata. So a matching version is like a very, very fine version of stratification. And one way of accomplishing this is to match each individual to 1 or more individuals of the opposite treatment sign, but who are similar in terms of their covariates. So the idea behind matching is to make, again, my treatment and my covariates independent in my matched sample. Right? I want to create a sample in which the treated and untreated individuals have the same or very, very, very similar distributions of the covariates. So if I had N1 individuals who received the active treatment, I want to select N1 controls, or the alternative treatment group, who are most similar in terms of their propensity score. Why choose the propensity score? Because it's a 1-number summary. It's an easy way of summarizing all of those covariates. Okay? But I also want to find pairs for the N0 controls. So this is a bit like the question that came up earlier of, well, why am I imputing these counterfactuals? What I'm trying to do here is for each treated individual, I'm going to find the closest untreated individual. And when I say closest, I mean the most similar in terms of their covariates, so that that individual's outcome can act as the counterfactual, right? I want to find the person who is most like me, but with the opposite treatment. And then I'm going to use my observed outcome and their observed outcome as the treated and untreated counterfactual pair. And I do this for everybody. So it's almost like I'm doubling my sample size. Just to say, although I'm doubling my sample size, there's lots of correlation in there because, of course, I am repeating individuals' data, and we do need to take that into account at the standard error calculation. Okay. So we can use this sample then to estimate an average treatment effect, because what we've done is we've created these matched pairs where the covariate distributions are very, very similar. so that the only thing that differs between these matched pairs are the treatment allocations. So with a simple matching estimator, we can just use the difference in the mean outcomes for these matched individuals. So we can think for any given individual, we're imputing their counterfactual by taking the outcome of their matched pair. We can do this with multiple matches too. We don't need to do one-to-one matching. We could do 1-to-3 matching, for example, but one-to-one matching is pretty common. So how do we actually accomplish this? Well, we need to choose some matching criterion. Often this is something like closest in terms of propensity score, or within some small caliper, so within 0.1 on the propensity score scale. We then evaluate whether positivity holds. Do we actually have overlap? Okay, if we do, then we can implement our matching method given our criteria, and we can evaluate the quality of the matched sample. And this is another question that came up earlier. How can I tell if I'm doing a good job? So this evaluating the quality of the matched sample, what we're looking for is to try to see whether our covariate or our confounder distribution is similar between the treated and untreated individuals after matching. And if it's not, then we've done a lousy job. So we need to go back to our step 1 and choose some other matching criterion. So not necessarily, for example, a caliper on the propensity score. Okay. But by conditioning on the true propensity score, this implies that our groups are balanced. So we can use this procedure to actually evaluate our propensity score model itself. So I'm just going to talk through each of these steps and give you a few visuals to see what it actually looks like. So in applying a matching criterion, a matching criterion is simply a rule that assigns the values of a covariate distance for individuals in the opposite treatment group. So I've got my Z equals 1 and my Z equals 0 group. I need to assign a distance between individuals in these. One way of doing this would be to simply look at the distance just on the numeric scale, real line scale between their propensity scores. There are other matching criteria. So you could look at the vector norm for the vector of their covariates. Prognostic scores have been used, so models for the outcome given covariates rather than the treatment given covariates. But basically, we just need some way of measuring how similar people are. And as I said, distance in the propensity score is one method that is often used. Once I've done this, I want to check my positivity. So one way that I can do this is by plotting my propensity score distribution in my 2 treatment groups. So here I'm looking for overlap. And of course, these distributions are different. That's not surprising, right? In the people who are not treated, it's less likely that they are treated. In those who are, it's more likely that they're treated. That's okay. We're not looking for similarity of the distribution of the propensity score. We just want to make sure that we don't have, big gaps where there's nobody in one group and there are in the other. Do I have some questions coming up?
Yeah, heads up, there's 10 minutes left, so it's up to you if you want to just leave them for the end, but I just wanted to let you know. I mean, you do what you think is best. All right, there are a few questions.
I think I'll leave them for the end so I can get through a little bit more. But I've got a lot of pictures coming up, so I'll try to wrap it up quickly. Thank you.
Good.
All right, so we check our positivity if we had any gaps. So for example, if this distribution cut off at 0.5, that would imply that everyone up here has no counterpart in the untreated group. And so we really shouldn't be making comparisons because these people are too different from their controls. So that's the idea of truncation, is choosing your sample so that you do indeed have data and you're not extrapolating well beyond the range of your data. There are lots of different matching methods. I won't go into the details of these, but there are different choices. Probably the most interesting part, I think, is to assess the balance, to see whether our propensity score is giving us what we want. Because what we want is to remove confounding. And if we've removed confounding, it means there's no relationship between our confounders, our X's, and our Z's in the analytic sample that we have created. So the distribution of the X's for those who are treated and for those who are not is the same in the analytic sample that we have created. Okay. In practice, we don't actually look at the joint distribution over all the covariates, but rather we look at marginal distribution. So we look at one X at a time. There are different ways of doing this. Probably the most common way is simply to look at the standardized mean difference. So we look at the average outcome, the average of the covariates in the treated minus the controls. So we're looking at how far apart they are divided by a pooled estimate of the standard deviation. We can also look at variance ratios. We can look at empirical CDFs. But really what we're looking for is small differences between the distributions of the covariates between treated and untreated. And just to give you an idea of what that diagnostic looks like. So this is from a real data set. I'm plotting the standardized mean difference along the x-axis. So this is giving me a measure of how far apart the mean of my covariate distribution is relative to the variability. In the red, I have my original data set, my unmatched sample. And in this blue column here, or line, I guess, not column, I have the analytic sample after matching. So what you can see is there are some covariates that are just wildly different between the treated and untreated groups in my original sample. But after matching, I've managed to create a sample where really there's less than a 10% difference in terms of an effect size measure, or my standardized mean difference between my treated and control groups. So that means that if I see a difference in the outcome between these two groups, probably I can attribute that to the treatment, because there's very little difference in any of these other covariates between these two groups. So this is how we assess balance. And this is something that is easy to do with propensity score methods. We can do this within strata if we do stratification. We can do this in our full sample once after matching. I think I will skip over the one last method I wanted to talk about, which was weighting. But we can also look at these standardized mean differences in reweighted samples. And so this is one real advantage to the propensity score that we don't have with regression, because it allows us to diagnose how good a job we've done at achieving this balance in confounders or in covariates between our two treatment groups. So I had one last method I wanted to talk about, which is inverse weighting. I think I will skip over this, but the idea behind inverse weighting is much like the sort of weighting, Horvitz-Thompson weighting that is done in survey sampling. I'd be very happy to make my slides available afterwards for anyone who wants to take a look. So I'm going to skip over that, if I may. And then just finish off with some key considerations for propensity scores and causal inference in general. So important ideas in causal inference when working with propensity scores is that we do need the propensity score to be correctly specified. So in regression, we need a correctly specified outcome model. With propensity score methods, I need to be able to accurately measure how treatment is allocated. Okay, so I need to identify the confounders. I don't need to adjust for things that just predict the treatment but aren't real confounders, so they don't affect my outcome. I need to get balance. I can test for balance in the covariates I have with those standardized mean differences. I can test for positivity, and I have to be a little bit careful in model selection, because traditional model selection approaches will specify or will preferentially select things that are really good predictors of the treatment, not necessarily select things that are important confounders. So that's an important distinction to be aware of. So again, that's just simply repeating that. We have to be very careful with our model selection techniques. I would avoid model selection unless I really need to, because I want to prioritize confounding removal or confounding elimination through my propensity score. There are methods known as causal discovery that try to discover whether variables are confounders. They are okay, but I would say they're no substitute for knowing the context. I know I'm like a broken record in this, but I just think we cannot apply real statistics in a vacuum. We need to know the substance area. And finally, don't assume you have balance. Check it. We can calculate these standardized mean differences or empirical CDFs. So it's really important to check whether we've actually done that. Just saying I used a propensity score isn't good enough. You actually need to check whether it's done what you think it has, which is give you balance. So even in simple settings, there are lots of different methods or techniques that could be used to provide causal estimators. Causal inference is not one technique. Causal inference is not a propensity score, but rather it's a framework for how to carefully approach an analysis to try to reduce imbalances and therefore reduce bias in the estimation for a given treatment effect. So one treatment at a time. So just to quickly finish off on some of those ideas from Bradford Hill, I think one of my favorite quotes of his, and I keep coming back to this, and I think maybe it's perfect for the Statistics Without Borders, where I saw that we have people from all over the world joining here. He says the statistician must learn a great deal of medicine. He's talking about medical statisticians, and not only have facility of speaking in 2 languages, but he must be able to think in 2. And he's talking about thinking about statistics and medicine. So this idea of being bilingual, this context is critical. The subject matter is critical. You need to be able to think about the underlying data distribution and draw these causal DAGs or these diagrams. So I drew a very simple one, but sometimes they can get a whole lot messier. There's usually more than one confounder out there that you need to worry about. So it's hard to think about these, and it's not something that can be undertaken casually. And we may get them wrong, that's okay. But the nice thing about these is that they make it explicit what assumptions we are making about the underlying data generation. Now, although I keep pushing context, he does remind us we can't know everything, but we need to know enough to be able to talk with the people we are working with. Otherwise, he says, if the blind lead the blind, shall they not both fall into a ditch? Okay, we need to know a bit of medicine or a bit of the science that we are working in. The scientists need to know a bit of what we are doing so that we can collaborate effectively. And so I will just skip over that and simply end by saying that Rubin's framework helps us formalize causality and think about just changing one thing at a time. These counterfactuals or these hypotheticals, they're what if quantities, but we don't actually need them. They just help us think about what is the one thing we want to change. We can actually get causal estimation or causal estimates by design. So with randomized trial settings, they guarantee balance as long as we do our randomization well and we have good compliance. But if we have non-experimental data, we typically need some modeling or design in terms of matching to account for confounding and other biases. So I've covered a few of the methods in the simplest setting, a continuous outcome and just a binary treatment, the balance checks that we can do, but there are many, many more techniques out there. And of course, many, many more settings in which we can apply causal inferences. So if we think back to Bradford Hill's criteria, I think a lot of what he was saying actually fits in the framework of what we've talked about today. He's talking about the strength of a relationship. Well, if you've got a huge relationship, maybe you can't explain it away by confounding. Temporality, we can assess through DAGs, but again, what he's getting at in many cases is this idea of bilingualism, understanding the context in which we work. So although he's less explicit in his statistical formulations than Rubin, and probably not the first place to go to for learning about how to implement statistical methods for causal inference, I still think he's worth revisiting because he has important insights in terms of how to think about applying these and collaborating with scientists. So we are trying to formalize these assumptions and make them as clear as possible. And I really think that the work we do as statisticians is incredibly valuable, and the stakes are too high to do it badly. Thank you very much. And I'm sorry I'm right on 30, but if people want to stick around, I'm willing to. I'm very sorry to go right up to 30.
Thank you so much, Erica. So I guess it's time for those who want to stay for the questions, to stay a little bit over. Alex, should we make some announcements first, you think, or?
No, I think Erica can address the questions if she has time. A few questions, at least about, I don't know, 3 minutes or so.
Okay. Sure. I mean, just given that other people might be jumping off, do you want to announce the next one or anything?
The next webinar will probably be on July 26th, and it will be about modeling infectious diseases. Please follow our website for the formal announcement. And thank you for coming today. And thank you, Erica, most of all, for a wonderful presentation.
My pleasure.
But go
Thank
ahead.
you so much. Let me see now. I will try to tackle the questions that I haven't yet answered. So since confounders precede the outcome, it sounds more like saying we want to capture causal variables. I don't know that, just before I finish reading the end of the question, I don't know that there's a formal definition for what constitutes a causal variable. Where's the place for random error? I mean, random error, I view as all the things we cannot explain. Usually, or we would hope that it is simply capturing things that explain our outcome, but are not true confounders. But there is no formal definition of what constitutes a causal variable. I guess we could think of confounders as causal variables, but we have other types of variables besides confounders. We have what are known as instruments, things that predict the treatment, but not the outcome. We have pure risk factors or precision variables that predict the outcome, but not the treatment. We might have effect modifiers, things that affect or create treatment heterogeneity, how the treatment affects, that may or may not be confounders. We have mediators. So we have lots of different variables. Unless something is pure noise, it could be seen as a causal variable in that it is part of the underlying data generation. For the propensity score, how is the uncertainty from the propensity score model propagated to the estimating treatment effect? That is a great question. So this can be done in a couple of ways. It can be done using projections. So if we want to calculate asymptotic variances, we can do this by projecting into the tangent nuisance space. If you're interested in this, there's a great paper by, I'm forgetting it. It's a Biometrica paper by a couple of Japanese authors. Somebody in Yaguchi. I'm forgetting the first author. I'm really sorry, but it's also following sort of basic methodology of projections into nuisance spaces that you could find in Wellner's textbook on asymptotic statistics. Or if you want to take the easy route, you bootstrap the whole procedure. So fitting the propensity score as well as the outcome. Or because Alex is staring at me, you take a Bayesian approach and that incorporates it naturally, but you need to be very careful. And in this case, I will give a shout out to Alex and my colleague, David Stevens, because it's very nuanced in a Bayesian perspective. It's not difficult, but the literature is still pretty new. So I would advise you to read work by Stevens on Bayesian causal inference. Earlier question about the BOGO and the lack of pre-intervention data. I'm investigating an augmented inverse probability weighted estimator. Is this a good technique for causal inference? So I'm very puzzled by the no pre-intervention data. If you have no pre-intervention data, none whatsoever, I cannot see how you have measured all your confounders. So AIPW or any form of propensity score-based methods, which AIPW is a part of, does require modeling a propensity score, which requires the no unmeasured confounding assumption. So if you have no pre-intervention data, you can't model a propensity score. So maybe there's something nuanced about this specific question that I'm missing, but you absolutely need your confounders. All of the methods I've talked about today rely on the no unmeasured confounding assumption. There are other methods known as instrumental variable methods that don't make this assumption. They have a whole host of other equally strong assumptions. They're just different ones. How does inverse probability weighting fit in? So the way that works is basically we fit again our model for the propensity score, and we use the weighting to upweight or downweight people given how unusual their covariate distributions are. So if my covariate combination is very unusual for my treatment allocation, then I will be upweighted. Or similarly, if I'm super common, I will be downweighted. So the idea is that in our weighted sample, we are again up or down weighting people to induce this balance in the covariate distribution. How do I evaluate the support for an empirical distribution if it has many dimensions? So when we are looking at common support, when you say evaluate the support, I'm assuming this means positivity. We tend to look at positivity or overlap just in the propensity score. If you have very high dimensional covariates, then you will very, very high dimensional, more than dozens, or a very small data set, you may indeed need to do some model selection in your propensity score. There is literature on high dimensional propensity scores and how to do this. But it's, as I said, you have to be careful. You can't use standard model selection techniques for the propensity score, because standard model selection techniques optimize prediction of the propensity score, not optimizing balance. And that's the goal of the propensity score. Can we use the propensity score in observational studies? 100% yes. First time I used a propensity score. Great. I like this. The first time I used a propensity score was my MD colleague who took the lead working through the papers to figure out how to do it. It showed me that this approach was pretty intuitive even for non-statisticians. That is a wonderful note to end on. Thank you very much. Thank you for your patience in letting me run over.
Erica, thank you so much for a wonderful presentation. I would like to remind our attendees that the recording and the slides will be available from the CIRS website. Bear in mind that this is an initiative of the American Statistical Association. Donna had to leave the call, but without her, this would not be possible. And without the American Statistical Association, this wouldn't be possible. So consider joining the American Statistical Association. Again, thank you so much. And we hope to see you on July 26th. Visit our website for updates. It will be on infectious disease modeling, probably. Thank you.
Thank you so much.
I'll stop recording.